So Harald is going to talk about one of the other important topics in this field, which is how to design organic semiconductors to improve their performance.
Yes, thank you very much, Professor Siringhaus, and thanks a lot also to Jochen for having me at this really wonderful workshop. Now, in the last couple of days, you've heard many great talks, a lot of them about very clever ways of calculating in a theoretical computational setup, the charge transport properties of organic semiconductors, taking into account the different regimes and all the different complications that arise from, well, the peculiarities of organic semiconductors. Now, this is not one of these talks. By that, I don't mean that we're not doing anything clever. I hope we're doing. By that, I mean that instead of trying to really calculate quantitative properties, we will be looking at things on a bit from a more of a trend-wise perspective. So trying to find so-called descriptors, things that we know from theory that need to be in certain ranges to make a material good, and then use the machine and ultimately teach the machine to find good new organic semiconductor materials. Now, when I'm talking about organic semiconductors, what I actually mean is small organic molecular crystals, small-ish, as it will turn out later. We're not currently working on any polymers as such. Now, I probably can skip over the introduction why organic semiconductors are a cool thing to do and go right into the main question. Given the huge wealth of potential organic molecules, even organic molecules with some sort of, for example, with some sort of ring systems where we can actually bring charges on, how do we find the right material? And this is actually not a very simple question, because there can be very many materials, as I'm going to talk about in a second. Now, what we're actually looking at is obviously, again, some form of conductivity. Mainly, we want our material to actually be able to conduct charges. I'm not currently specifying if electrons are holes, but suffice to say what we're mostly within this talk be focusing on is the transport of holes, but would work equally well for electrons. So generally, the conductivity is defined as the density of charge carriers, the amount of mobile charge carriers you have in your system, times their mobility. And as we've heard in the past, it can be a real pain in the neck to actually calculate the mobility, given that that is highly material dependent on what kind of regime you're actually in. So this is not what we're going to try to do. Instead, we're going to be concentrating on so-called descriptors. And these are properties that are computationally accessible, but do correlate in some fashion with the quantity that we want to optimize the conductivity. And the three ones that I will be talking about in this talk are the energy alignment of, in our case, the HOMO level with a reference electrode. The reference electrode in our case will be gold. This we want to match as well as possible, such as to minimize any energy losses there. The reorganization energy, the energy it costs you to reorganize the system, to repolarize the system after something has moved. Now, this you might know from hopping theory, but one can show that it is slightly that is also slightly correlated to the electron-phonon coupling in a more advanced model. And this we want to actually minimize. This cost us energy, we want to minimize it now. And the last one is the electronic couplings between the sites. Again, most well known from any Marcus type hopping theories, but in a simple tight binding model, one can easily show that already, that this HAB, this coupling, also corresponds to the bandwidth in, for example, a band picture of transport, and this you want to maximize. Now, for the first thing we did, and this is already a couple of years back, we focused on lambda and the electronic coupling, and we were asking ourselves, all right, now what happens if we take a very big database of organic molecular crystals? So we downloaded a portion of the Cambridge Structural Database and then calculated these two descriptors for the molecules in there. Now, these two descriptors are not equal in their computational cost. One of them, lambda, if you calculate just the internal reorganization energy of a molecule, is a molecular property, whereas the couplings, you need to actually take into account all the pairs that you can have in your crystal. So for reasons of efficiency, it is a bit more clever to calculate the cheaper descriptor first and already weed out all the things that are to calculate the cheaper descriptor first, to weed out the things that are unfavorable by this descriptor, and then only calculate the more expensive one here. Now, because you need to do some sort of geometry optimization, I said that the wrong way around earlier. If you're doing some kind of geometry optimization for the reorganization energies, this in this case would be the more expensive one. So we first calculated all the couplings, then weeded out all the crystals that have rubbish couplings, and then only for those that are good calculated. This approach is known as a computational funnel approach, because that is what we're doing. We're one by one going through our descriptors to try and arrive at a good set of molecules that would fulfill our properties. Now, the numbers in here are a bit old. We by now have a little bit more. And in principle, these are the results that we get here. So on top, there is the histogram of the couplings. And you see, well, the problem here is that most couplings are actually low. So that is actually quite a good initial screening parameter, because most of this database is simply not made to be organic semiconductors. They are medical drugs, they are explosives, they are pigments. They are not made for conducting electrons. So the second parameter, which does show some maximum at around 200 milli-electron volts, the reorganization free energy, this we want to then minimize. The final result can be presented in this kind of plot. So you have a 2D histogram, and then you would want to find things that are in the lower right half of this lower right corner of this graph, because then you have a high coupling and the low reorganization energy. And luckily enough, the well-known materials do find themselves in this graph as well. But based on that, we could now, for example, choose some promising candidates, which are highlighted here in red, to then give to experimental colleagues to evaluate. Now, this is quite nice. This allowed us to look at some materials people had not yet looked at for their semiconductor properties, to see if they would make for a good organic semiconductor. This is just a little bit unfulfilling, because the main disadvantage is this kind of approach limits us to those materials that are already contained in this database. If there is a good material that would look slightly different, but is not in the database, we would not find it, because we only screened a database. But this is where the actual problem comes in, because the chemical space of molecules, even small-ish molecules, is vast, with estimates ranging from 10 to the 16 to 10 to the 40 different molecules. And I think you will agree with me that even with cool computing resources available today, that is not something, that is not a database you want to screen with a computational funnel. So we need something more clever. The reason for that being that even if you can enumerate this space, meaning you can make all those molecules, you do not want to calculate at least one descriptor for each of these 10 to the 33 elements, as you would have to do in a funnel. Even if you pick some at random, that does not guarantee that you're going to find the good one. So you need something a bit more clever. And the method that we've been using, that we actually adapted from the pharmaceutics research, is an active learning model. So what do we do here? Instead of starting with a huge database of already known molecules, we just pick a very small population that basically we just need something to start us off to then make our molecules with, and also to train the machine, which then lets us predict the properties that we're interested in. I'll come to that in a second here, just the concept, because in principle, it is a very simple approach. What we're doing in this active learning is we're from this initial population generating candidates. So they're generating a couple of candidates that can be done in many generations, that can be done with some rules, which I will highlight later on. Then we use a machine learning model, because those are already quite tendentially many molecules. We use a machine learning model to pick for us, or let the machine pick, which of those are actually promising in terms of the descriptors that we coded into it. And this machine learning model we call the surrogate models for our descriptors. And then the machine, based on these predictions, picks some to then evaluate actually with DFT, calculate the descriptors, which if they're good, are included in our new population. If they're bad, they're also included in our population, just for the surrogate model to know what is good and what is bad. And then from there on, we keep on doing this for a number of repetitions until we have sampled the space of potential organic semiconductor molecules to hopefully give us a good result. Now, step one of this is we need to teach a computer how to make a molecule. And that is not as super easy as it may sound. So what we did is we looked at some very well-known examples that are good organic semiconductors. And then we figured out what kind of operations, addition of a ring or addition of a certain side group or shrinking of a 6 ring to a 5 ring, we would need to create all of these, starting from, for example, a benzene molecule. So turns out that only 22 operations you need for that. I listed them here just for completeness. The actual kind of operations are a little bit dependent on what kind of molecules you want to make. We have all of these molecules also in reverse, such that we could go back in principle to sample the space fully. Now, what that means is that with these operations in place, if we repeatedly apply them to a molecule, we can in principle generate a huge space of organic molecules. Now, the descriptors we're using in this case are a little bit different. So here we concentrated on the energy level alignment and the reorganization energy, and you might already see why that is, because in order to predict electronic couplings, you'd need a crystal structure, and we have not yet included a crystal structure prediction step in this active machine learning model. This is something we want to do in the future. Now, having those two descriptors, the one that we want to match exactly, the one that we want to actually minimize, we can define a fitness function of the reorganization energy and the alignment mismatch, which I called epsilon align here. And then just to know what in this fitness function would constitute a good and what would constitute a bad example, we again compared to known organic molecules and figured out that with certain weights in place, which are hyperparameters, which we optimized separately, will tell us that if our fitness function is better than -0.2, this might be a good candidate for an organic semiconductor molecule. So now, in order to actually fix those meta parameters and figure out if our algorithm is any good compared to a more traditional screening or morphing algorithm, we actually started with a test space. So what we did is we, using these operations that generate our molecules, we restricted the molecules in size. So we said that you shall not surpass a certain size of molecule, which restricts the whole space that we're sampling. So we restricted this space to 65,552 molecules, for which we then actually calculated the two parameters. We did that because this now allows us to figure out in this test set which of those would be the target molecules, the ones with a good fitness function, which our algorithm has to find. And now we can let our algorithm loose and see how many steps, how many evaluations it will take for the algorithm to find at least a good percentage of the target molecules. So yeah, in this test set, there's roughly 2,500 molecules that are good. So here in a little bit more detail of what's actually going on. So I already told you that starting from a population, we generate one or two or even more generations of molecules using our morphing operations. Then we use a machine learning model. This is a simple-ish Gaussian process regression, I'm sorry, which we're using to predict the values of these two descriptors. Now, in machine learning, you also need a way to actually represent what your structure looks like to the computer, so it can see, have I seen this molecule before? Have I seen something similar to it? And we're using some circular Morgan molecular fingerprints. So basically what that does is it looks at each atom and then looks one or two bonds away from it, and then memorizes the substructure and compares the amount of times the substructure matches between molecules, just very roughly speaking. So this allows us to predict the fitness, this function f. Based on this f, we can then let the machine pick new molecules to query. With querying, we mean do the actual ab initio calculation of the properties. Now, this is by itself would not be super efficient, because that would just minimize everything and we would very likely get stuck in a very small region of design space. Now, luckily, our GPR model has another advantage, namely the GPR model knows when its prediction is going to be bad. If a molecule is very different from all the molecules it has seen before, then the prediction is not going to be very good. So we know the uncertainty. But this is a very cool way of telling our machine to actually look for regions of design space which we haven't sampled yet. Because where the uncertainty is high, it means we haven't seen this type of molecule before. So the actual acquisition function by which the machine chooses to pick a molecule and do the DFT is this F. So either it's a very good molecule or its uncertainty is high. And in that case, it also wants to look at that molecule because it could be an interesting region of phase space. And then doing that over and over again. Now, in this graph here, and this is just a way of visualizing that design space. So in principle, what this graph does is every single molecule that we have, every single of the 65,000 and such molecules, they do repel each other in a 2D surface. But if, according to this fingerprint, they are similar, or no, sorry, if they are connected by some of the morphing operations, they are neighbors in this space, which then produces an attractive edge. So that's why it looks a bit exploded. So you have regions that are very similar to each other, but not similar to all the rest. And then they are very far away. The molecules marked in red here are the good ones. Those are the ones our algorithm should find. And we start out with a random initial set, and already a couple of them are in there. The blue ones are the identified molecules that are good, that we found through our active machine learning. And after 10 of these steps, a population size of 1,179, meaning those are the ones we did DFT calculations for, we now have identified already 500 of the good molecules. And doing that, we do find a very, very large percentage of the good molecules. So after 50 of these learning steps, where we have queried, where we have done DFT calculation on only 8% of that test space, we already found 80% of the good molecules. Now, there are some outliers we did not find, for example, this lower right-hand or top left-hand side. These are the ones that are very different. We probably would have to let our algorithm run longer for that. But now what happens if we apply this algorithm to an in principle unrestricted space? So if we lift this restriction of the size and now have a space that can go on forever until we just tell it, stop here now, that's enough molecules, I don't want to see anymore. Now, what we see here is the evolution of the median fitness function after each learning step. And you can see that already after 5 learning steps, the median is over this minus 0.2 threshold, which we semi-arbitrarily set as our threshold for a good molecule. The orange and the blue one here are 2 different runs of the algorithm, so with different initial conditions. Now, what that means is that we're very efficiently finding good molecules. Now, this would look very much the same in an evolutionary algorithm where things converge, but the advantage with us mixing in this uncertainty into the acquisition function, we're not actually, and this is the same graph now showing the distribution that we have, we're not actually losing any width in the space of our fitness function, meaning that we're always throwing in more molecules that might be rubbish, but that might lead to interesting new molecules. Now, the actual results are shown here. So these are the best predicted molecules, and you can already see something that I did not mention before. This actually has, we actually did a little trick. All the molecules are symmetrized. So our generation function is designed such that it only generates symmetric molecules in the hopes that this is a little bit closer to something that you can actually make. Now, concentrating on just this level mismatch and the reorganization energy, even the internal reorganization energy, obviously. So this has shown us that in principle this can work. This kind of search is quite a good one, is quite an efficient way of designing molecules. I would not necessarily go to an experimental colleague and ask him to make that, because this is going to be the next and greatest organic semiconductor. The reason for that being that by necessity, we left out quite a lot of things. So the next steps, the ones we're working on currently, would be to actually include a structure prediction step to, first of all, check, can this thing even be a stable crystal? Then look at the couplings, because that is something we have omitted completely from this study so far, and look at all the other interesting properties here. Now, the advantage of this method is that we don't actually need to calculate the descriptors, even descriptors based on the structure of a crystal, with the same kind of frequency that we do the others, because we could simply tell it, well, query the expensive ones less often. This would make the overall progress in these descriptors a bit slower, but would still allow us to go into regions of phase space that have very good values of these descriptors. Now, I think my time is actually already over, and Professor Sieringhaus said he has to leave on time. So with this, I finish here. I very much thank the people who did the work. First and foremost, Christian Kunkel, who did all the fancy the fancy machine learning things, and thank my collaborators and the funding agencies and you for your kind attention.
Thank you very much, Harald, for a very interesting, fascinating talk. There are quite a few questions in the chat, and I think I have to select a few questions. And the first one that I wanted to select was whether the model generates equilibrium structures or whether you have to optimize promising candidates afterwards.
So that is a very good question, actually, because I glossed over it all completely. What I only showed you the 2D graphs. The model itself only makes the 2D graphs. Our morphing operations work on this graph structure of the molecule. Now, obviously, you can't work with that because some of these molecules are actually quite floppy and flexible. So there is in between, and I did not mention that, a step where we actually look at the different conformers of the molecules with a, not with DFT, but with extended tight binding, where we actually search for the lowest conformer structure of each of these molecules. An equilibrium structure, we have no crystal structure in there. So this is not, these are gas phase calculations.
Great. There were two questions on how you represent molecules, whether there is a unique molecule representation, whether you use a SMILE format or...
So yes, but within the SMILES format, we actually, because we need to be able to calculate distances between molecules. That is how machine learning always works. You have to be able to say something is similar to something it has already seen. So we're not using the SMILE strings directly, but as I said, we're using these molecular fingerprints where it compares substructures. For example, it goes through all the atoms in here, and I see, okay, many of these atoms have 3 carbon neighbors. So this would be, you probably can't see my pointer, and I can't. Okay, I don't seem to be able to do. Wait, no, that's eraser. I don't have a pointer here. I'm sorry. All right. So yeah, what that does is, in principle, we compare the substructures contained in this molecule. The details are given in this paper here at the bottom.